Now, when our eyes are actually observing something, and I think you already realize this, our eyes are actually only limited to seeing three colors, and we infer all the other colors from that. And the reason is that we have three pigments in our eye. One is able to absorb red light, one able to give us an absorption from green light, and the other gives us one from blue. And so when the photon gets absorbed, it creates a little signal. And so we say, oh yeah, right, that was green light hitting my eye. And we say, hey, that's green. In other words, the object is reflecting that light, and it's getting to our eye, where we then perceive it. Now, thing is, there's going to be a whole lot involved in exactly what goes into perception, and that's going to be a whole topic that's well outside of analytical chemistry. It's really interesting in its own right, and anybody who has artistic interests would do well to understand a lot about that, because each pigment that we have is going to have a range that it absorbs. And in that range, it's going to absorb a different amount of light at different wavelengths. And the rest of it's going to typically be reflected. Now, when that happens, it gets to our eye, and it gets kind of binned in as either red, green, or blue. But based on where exactly it is between those, it changes the ratio. So suppose that you've got a light that's, well, let's see. Let me get my pen up here. Suppose we've got something where this is the absorption range of one pigment, this is the absorption range of my neighboring pigment. If I go for this light, we'd say, oh gee, it's stimulating my red. It's also stimulating the green pigment a little bit, so that's probably going to be something like a reddish-orange color. Now if it's over here and it's barely stimulating the red at all, let's just get it down to baseline there, we'd say, yeah, that's a green light that I'm looking at. So the spacing of these pigment absorption spectra ends up mattering, and so does how well we can perceive that photon when it hits our eye, give us a red signal, and give us a green signal. So it's going to be about brightness of the photon and also what color it is. So there's all kinds of effects that are happening there at once, so the perception of color turns into a very complicated idea. But what if we just try to distill it down to a much more simple case? After all, that's what we're trying to do in the sciences most of the time, right? We're taking a complicated system, and we're trying to give it a much more simple explanatory model that still has important power. Let's just say that we went for a black and white photograph instead, where just the intensity of each of these photons hitting our detector is giving us a signal. Now, of course, you've still got lots of messiness there. If I have a pixel count that goes up to 1,000, I know they usually go to like 1024, but we'll make it easy. Let's say that our pixel numbers go from 0 to 1,000. One pixel that says 1,000 is going to be very bright. A pixel that says 5 is going to be very dark. Okay, but how much intensity of red light did you need to get each of those numbers? How much intensity of blue light did you need to get each of those values? Blue light has more energy in it. Probably was better at kicking an electron off of your detector and actually giving you a measurement, right? Well, all those things are certainly going to be important, and that means that every detector you're going to have out there is going to have this whole performance profile where you have to consider the wavelength and the efficiency at that wavelength, and also any specificity at that wavelength. So there's a whole lot of factors playing into all of that at once. And that's front-loading some of the conversation that happens throughout this chapter and some of our subsequent ones, and also a lot that happens in instrumental analysis. But let's go ahead and take another look at something, though. All that complication I just gave you was just inside of the visible range. What if we take a look at that same scene, but we set up some filters and we pick a good detector that's able to see in the infrared? Well, if we take a photograph with infrared light, you can see the exact same features and it looks the same at first. But then you actually start looking at it a little more. And notice all these reflections that you're seeing in the water right now? You're not seeing them as much anymore. This little tree sitting over here on the side really is jumping out now that it's glowing white. Same with this big tree that was already pretty obvious. The pine tree in the back almost looks like it's snow covered now. In other words, all of these things are doing a really good job of reflecting infrared light, and it's getting to our eye or our camera. The water isn't doing a good job of reflecting it, which probably means the water is absorbing at that specific wavelength. Now you can see that the hills in the background, same sort of things. The clouds in the sky look a bit different. You see a difference in the haze. There's going to be a lot of differences in how things are perceived when we're actually looking at them with infrared light. But the key part of it I want to point out. Okay, so it looks different, but did it behave differently other than, the efficiency of our detector and all that? Well, no, a photon is a photon is a photon. So it doesn't matter where in the electromagnetic spectrum you're at. The energy of the photon is going to change, but how it behaves is not. Your lens is still going to focus light. Now, it may not focus it the same way as you get to other wavelengths. It may not bend it as much, or the material may stop interacting with the light at all, which just means you use a different material for your lens. Remember, you can still bend a radio photon. You can still set up some sort of a lens for a radio photon. You can still set up lenses for X-ray photons. You can still set up sunglasses for all of those colors as well. You can have sunglasses that are UV absorbent so that they don't transmit any ultraviolet to your eyes. There's all of these things. But a photon is a photon is a photon. Now what happens with that packet of energy once it hits a molecule, that changes. But a photon still propagates through space. And it still gets absorbed or not absorbed by a material. It can be scattered by a material, but it's going to behave the same as any other photon under the same condition. In other words, if a photon scatters, then it's scattering. You use the scattering equation. That's what I mean when I say a photon is a photon is a photon.